Okay, so this is Unit 7. And Unit 7 is really just all about exponential functions and exponential equations and how to solve them using what is going to be a new term, which is logs. So, and we'll get to that a little bit later, but today we're just going to go do the basics of exponential functions. You may have briefly talked about this in your Algebra 1 class, but today we're going to go obviously a little bit more in depth. So an exponential function has the form, and it's a specific type of an equation, which is y equals a b to the t power. And all of these have meanings. A is your initial value. B is, and this is something you're going to become familiar with here, is called the growth factor. And it'll always be b equals 1 plus or minus r. Depending on how it's growing, and you're going to have this plus or minus. So because we're going to talk about exponential growth and exponential decay. So this r right here serves as the rate, and it's the rate that it's growing or decaying as a decimal. So basically, if the growth factor will be over 1 if it's growing, and it'll be less than 1 if it's decaying. And you'll see an example of this as we get down here. And then obviously t is pretty universal here. T is going to serve as time. And it could be any time, hours, days, whatever the problem defines. So that's what everything looks like. This you may have seen something similar to this, the initial value, and that's something new. But this whole growth factor idea, that's what we're going to talk about first here. So depending on that value of b, we have exponential growth or decay. If the value of b is greater than 1, you have growth, meaning the values will increase over time. And if you have a number that's less than 1 and non-negative, right, it can't be negative, it has to be a positive number. But if it's less than 1, like 0.2, 0.3, 0.4, whatever, then you have decay, meaning the values will decrease over time. So, and this is what I just read here, depending on the value of b, so this is what we're looking at here, you have exponential growth or decay. In exponential growth, your b value will be greater than 1, and in decay, your b value will be less than 1. And this is sort of what it looks like. So exponential growth, it will increase over time. And if you know anything about exponential, like population growth and stuff like that, you get this spike here, and that's sort of traditional exponential growth problems where it grows more and more rapidly over time. Again, this is when your b value is greater than 1. And then you have exponential decay problems where over time they will decrease over time. And this would be something that might be maybe the depreciation of a car or something like that. How it depreciates very rapidly, and over time it depreciates less and less. But the graph has this traditional sort of downward trend. And this is if your b is less than 1. So let's look at a few examples here. Now obviously, and just to go back here, just a reminder, and you may want to put this in here too. It can be negative. I mean, when I say by b is less than 1, I don't mean that anything less than 1, like -2, -3. It does have to still be a positive number, so the value will be between 0 and 1. Okay, so first we're going to identify our growth factor. So, and since there is no a, it looks like there's no a, you have y equals a times b to the t. There is no a there, so we assume the a to be 1. So what this really looks like is 1 times 2 to the x, where this serves as our initial value, and this serves as our b, which is the growth factor. Since that 2 is greater than 1, you have exponential growth. So what we should see here is an increasing graph over time. Now we can quickly do this filling in this table. It's real easy. When the equations are this short, you may be able to just plug it in, but I like to make things easier, and I'm going to use my graphing calculator. So what I'll do is I'm just going to put in this equation into my graphing calculator. So y equals, I don't know why we have an inequality here. So, there you go. So I'm going to put this in there, which is y equals 2 to the x. So 2 exponent and x. So you see I have the x there and the exponent. And so you can graph it if you want to and take a look at this. And my window's all messed up. So I'm going to do zoom 6. But you can see the trend of this graph. Very traditional sort of exponential growth. But to get the actual values and graph it, I'm going to go to table and look at my table. Notice how the numbers increase rapidly sort of over time. And so again, that's another exponential growth trait. So we're just going to fill in this data table. So we go to -2, and it looks like -2 is 0.25. So -2 is 0.25. It looks like -1 is 0.5. 0 is 1. 1 is 2. And 2 is 4. And 3 is 8. And so we fill all in, and so we don't need that anymore. Okay, and we can actually graph this. So at -2, the value is 0.25, so it's going to be really close to that axis. And then -1 is 0.5, a little further away. 0 is 1, 1 is 2, 2 is 4, and 3 is 8. 3, 1, 2, 3, 4, 5, 6, 7, 8. So again, you have this very standard sort of graph. And the one thing to look at, and I didn't really show this when we looked at the graph, notice how the line here never ever crosses the x-axis. Okay? You can't have negative values. So if I start with a base of 2, if my base is going to be positive like this, then there's no way, no matter what exponent I put in, I'm going to get a negative number. And if I look at the table, we can see that as I go more and more negative, it never gets to 0. It just keeps getting closer and closer to 0. These -7s, these are zeros in front. So 0.00000000012. So it's getting closer and closer to 0. So it's important that on your graph, when you go to graph this, that you be aware that you can't cross the x-axis. It should look something like that. Okay, a couple things to also be to sort of observe here is right here, when x is 0, you actually have your y-intercept, which is also right here. This would also represent your starting amount. Since we started at 1, our y-intercept will be 1. So that sort of correlates there. But the point here is going to be understanding what is exponential growth versus exponential decay. Being able to pick apart what is the initial value as opposed to what is the growth factor. And then being able to put this into a graph. So let's try the second one here. So on the second one, okay, notice here that I do actually have an a. Y equals a times b to the t power. where this is my initial value. It should correlate with my y-intercept. And you have a fraction in there. So in this case, my growth factor is 1/3, which is actually less than 1, which means that this is decay. You'll see when we go to graph this, the graph will be decreasing. Okay. So here, y equals, I'm going to do 2 parenthesis, and this is what's cool about these newer, fancier calculators. I can put a fraction in there, 1 and 3. Close those parentheses to the x power. What's nice about the new calculators is you can actually make it look like it actually looks on the paper. So 2 to the 1/3. You could do this in an older calculator if you just did 1 divided by 3 in the parentheses. It's the same thing. And when I graph this, you'll see that again, just like the previous example, or the examples up here, is that it has this very traditional sort of downward trend. But again, just like the other one, it never ever crosses the x-axis. Because the base here is positive, there's no exponent you could ever put in that would ever make this a negative number. So you can't have a negative values, which is why it just gets closer and closer to 0, but never actually crosses. So let's put this in a data table. I got really far away here. I gotta go back. -2 is where I start. -2 looks like it's 18. That's obviously not going to fit on my graph. -1 is 6. 0 is 2. Yep, it does correlate with that initial value. 1 is, notice here that it gives me fractions. That's kind of cool because I used the fractions in the problem. 2/3, and then you have 2/9, and then 2/27. Basically, just the fraction gets smaller and smaller and smaller, so closer and closer to 0. So as we graph this, obviously I can't do 18, but I can do -1 is 6. 1, 2, 3, 4, 5, 6. I can do 0 is 2. 1 is 2/3, and then it just keeps getting closer and closer to 0. So the way that this looks, or like that. And so that's graphing exponential growth and decay problems. Next page. So now we're going to use sort of our knowledge of exponential functions to do some modeling or apply them to real sort of life situations. There are a ton of models that use exponential models, from population growth to half-life of radioactive material to bacteria growth to radioactive decay. I already said that. But there's a ton of examples that use exponential functions. So we're going to just use a couple here to model this. So, first of all, the number of bacteria in thousands, okay, always got to be aware of that, in thousands, those are our units, in a culture can be approximated by the model of y equals 100 times 1.99 to the x power, where t is the number of hours the culture is incubated. Couple things to notice here. Our initial value obviously is 100. That's what the 100 represents. And then the 1.99 is greater than 1. So yes, we're going to have growth. And if you know anything about bacteria, you probably already understood that. So A says, does this model represent exponential growth or decay, which is sort of what we just talked about. Because, so it's growth, obviously. But why is it growth? It's because factor is greater than 1. Okay. We have factor is 1.99, which is greater than 1. This second one says to identify the growth factor of this model, which we already did. It's up here, 1.99. So 1.99 equals B. Then identify the hourly percent growth. One thing that you need to understand here is there is a difference between the growth factor and the percent growth. Okay, percent growth or decay and the growth factor are different. Remember from the notes on the previous page. If we sort of revisit this real quick, you'll notice that B equals 1 plus or minus R, where R is the rate or the percent rate growth as a decimal. So if we want to know what the growth rate is, the percent rate of growth, we can just use this equation here, B equals 1 plus or minus R. So on this page, I'm going to use B equals 1. Now because we already know that this is growth, I'm not going to use the minus R, I'm just going to use the plus because minus would be decay. 1 plus R. Well, we already know that B is 1.99, so 1.99 equals 1 plus R. I simply just subtract the 1 over, and I get R equals 0.99, which equals a 99% growth. 0.99 is 99%. Okay. So that percent growth is plus. And then we go to C. It says estimate when the number of bacteria will be at 1 million. So y equals 100 times 1.99 to the x power. We're trying to find x is going to serve as t because in our function that's what t is. It's the exponent, so that x will be t, when y will be the number of bacteria. The number of bacteria, y. So when it asks for the number of bacteria, it's really asking for y. So in our function, y is going to serve as 1 million equals 100 times 1.99 x. Okay. So here's what we do. So we right now we can show you ways of approximating this. Right now we're going to get to this later in this unit. Right now you don't know how to solve an equation where the x is in the exponent. This is an exponential equation and we haven't learned those yet, but we can approximate what this value is by using our graphing calculator. It won't be exact, but it'll be an approximation. So what we need to do is when we're solving for this x values, we need to isolate this exponential part, the base and its exponent. So the 100 we can move over simply by dividing by 100. Divide by 100, you get 10,000 equals 1.99 to the x power. Now here's what you do. In your graphing calculator, you just put one side into your y1 and put the other side into your y2. It will form two graphs. Wherever they cross will be what x approximately equals. So again, I'm going to take this and I'm going to put the left side into, and technically you could have done it up here, but it's just a little easier when it's just one term like this. On the left, I can, y1, I'm just going to put 10,000. Okay, and then I'll go to y2, and I'll put this exponential part, which is 1.99 to the x power. And so I'm going to graph this, and you see the exponential. Now obviously because my graph is at y equals 10,000, I'm obviously going to need to raise my y to at least 10. I mean, this y equals 10,000, and my window only goes to 10. So if we go to window and adjust this y maximum, now we need to at least be at 10,000, so I'm just going to use 20,000. And graph. There's the 10,000 line. And here is the exponential line. Oh, it just comes up just right here in the corner. So I do need to move it over. The x value does need to go in this direction. So I'm going to increase my x max. Let's go to like 20. I just went to 10, so now I'm going to go to 20. And when I graph this, there's my 10,000. And come on, exponential. There we go. Oh, and we have an intersection. Okay. So what we do, and we did this last semester, to find the intersection, you do second calc and go to intersect, enter, and then you just hit enter 3 times. 1, 2, 3. And it will provide that intersection. So it looks like, if we look here, that the x value is 13.38. So the approximate value, and we use that by these little squiggly lines, x approximately is going to be 13.38 hours. Okay. So in these exponential modeling equations, because we don't know how to solve an equation yet, where x is in the exponent, for that we use what are called logs, and we haven't learned logs yet. So we can graphically estimate this by isolating our exponential part here, the 1.99, to the base in the exponent, and just putting y1 on for this side and y2 for this side, graphing them, and then just seeing where they crossed. This is where they crossed. So that's how we graphically estimate the value of x. Okay. So we're going to do something similar for this next problem. Okay. And this is another type of question that I mentioned. The depreciation of a car. Cars depreciate exponentially, an exponential decay. Cars have a lot of value in the beginning, but quickly, as soon as you drive them off the lot, they lose value very rapidly. And over time, they don't lose as much as the car gets older, but they lose money or lose value rapidly in the beginning. The value of a car Y in the thousands in the see here. The value of y, where is that? The value of y in thousands of dollars when first purchased is $25,000. Okay. So the car loses 15% of its initial value every year, or T, years since purchased. So we're going to develop an exponential model for this. Couple things to keep in mind. First purchased, 25,000. So again, this will serve as our initial value. But one thing we need to keep in mind is that the answer, the dollars, the car is in thousands. So we actually only need 25. Because it assumes that the answer is going to be in thousands of dollars. So that 25 does represent 25,000, so we just need 25. The car loses 15%. Okay, loses would be obviously decay. It's going down over time. But then it also gives us that R value. Because it's decreasing by 15%, that is a percent rate, which is 15%, which as a decimal is 0.15. Okay, so we're going to write our problem here. So we have an initial value of 25, so y will equal 25 and then we have to put in b, which is our growth factor. Well, wait a minute. We don't have b. We don't have our growth factor. We need y equals ab to the t. Now we have a, our initial value, but we don't have b. Well, the good thing we have an equation for b. b equals 1 plus or minus r. In this case, since we have a decay problem, okay, we're going to be using minus. So b equals 1 minus the percent rate of change as a decimal. So minus 0.15. Therefore, b equals 1 minus 0.85 is 0.15 is 0.85. So our b value will be 0.85. And then to the t power, which is time. So there is our formula, y equals 25 to the 0.85 t power. So we got our growth factor. It is less than 1, so that means it's decreasing. And we started with 25, which represents 25,000. And so now we can solve. What will be the value of the car after 4 years of purchase? Well, 4 years is t, so y equals 25 times 0.85 to the 4th power. And that's just simple, putting it in your calculator. So just be careful to do your exponent first. We have to still be conscious of our order of operations. So 0.85 to the 4th power, and then multiply that times 25. Now do keep in mind that this does say 13, but it's not 13. Remember, it's in thousands. So if you want, you can multiply that by 1,000, and then that'll be the actual value. So looks like 13, and maybe I'll put this over here. So our value is, let me see. There's nowhere to put this calculator. Y equals, here, do it over here. Y equals $13,050, and looks like 16 cents if we round. There we go. And so that would be the value of the car after 4 years if it started at 25,000. Now, estimate when the car's value will be 8,000. So when is obviously t. So this is where we need to solve for t, whereas 8 is going to be the actual value of the car in thousands. So this is always something we have to be conscious about, and I know this is going to cause issues. When you have units in the thousands, you need to be aware of that. That's why this represents 25, and that's why this is going to represent 8, not 8,000. So y will be 8, which actually is 8,000, equals 25, which is actually 25,000, times 0.85 to the t power. So all I do is plug in 8 for my y value. But now we got to solve for t. So remember, we have to isolate. Got to isolate this. So I'm going to divide the 25 over. Cross this out. 8 over 25, I believe it's like 0.32 or something. 8 divided by 25. Yeah, 0.32. So this is 0.32 equals 0.85 to the t power. And I can put this in my y1. I could put this in my y2 and just see where they cross. So if I put this in there, y equals clear, y equals 0.32, and then you have 0.85 to the x power. You can't use t's in the graphing calculator, so just use x. Now when I go to graph this, there's obviously going to be a problem here, because my last problem was in the tens of thousands. This is obviously not. I'm putting in 0.32 as my y. So let's first go back to normal. So there looks like the line and the exponential. That's really hard to see. So I'm going to zoom in, and I'm going to place my cursor. You should have a little cursor. Can I see cursor? I'm going to put it looks like it crosses somewhere over here. So I'm going to zoom in right there. let's see. Okay, so we do have what it looks like it intersects somewhere in here, because you see it's above the line there, and then it comes below the line over here. So the intersection is somewhere right there. Now, good thing our calculator will do this for us. Second, calc, intersect, and then you just do that 3 times. 1, 2, 3. And it does find the intersection for us. Again, this is just an estimate. So when we go to find the answer here, and I just can't figure out a place to put my calculator, you will have t equals 7, it's like 7.01 years. That's when the car's value will be $8,000. Okay, almost done. Almost done. The last form of exponential equations is something that you're probably familiar with. We do this a ton in the Algebra 2 financial course, and that is compound interest. Compound interest is the most credit cards, loans, anything where you have debt, most things compound interest in some way. Your credit cards will compound interest every month. Your house or home loans or auto loans will compound interest daily. So this is used a lot, and so we're going to see, you can oftentimes use this to see how much interest you end up paying at the end of a loan, or how long it may take you to pay things off. So there's a bunch of applications for compound interest, which is another form of an exponential function. So consider the initial principal P, that'll be the initial amount, it's same in the previous equation, and that pays interest at an annual rate, okay, expressed as a decimal, compounded certain amount of times per year. The amount A in the account after t years is given by this formula. And so this is a modified version of your previous exponential function. And that is A equals P parenthesis 1 plus R over N to the NT. Now, a couple things to take note here. This is not something you're going to have to memorize. You'll be given a formula like this. You'll just have to know how to use it and where everything goes. A will serve as the amount in your account. I think of A as amount in your account because they both start with A, but technically it's your balance, whatever you have. P is just like your A in your exponential function. It is your initial value. We call this the principal. It's whatever you initially start out with in the account. The N is actually the number of times compounded per year. And T, again, T is just sort of universal, it's time. But more specifically, it's time in years in this formula. Okay. Oh, forgot one. R. R is what you might think it would be. R is your percent rate. And then it's as a decimal. Has to be as a decimal. Okay. So really, what's nice about these compound interest problems is you really just plug things in. There's no, nothing crazy difficult here. So we're just going to plug things in. So example 1, you deposit $9,000 into an account that pays 1.46% annual interest. Find the balance after 3 years. So you have obviously an initial deposit, which will serve as your P. You have a 1.46%, which is an R, but you do have to change that to a decimal. And then you have 3 years, which is time. And so I'm just going to plug everything in. Oh, and the last thing here is compounded quarterly. Okay, compounded quarterly, if you don't know what quarterly means, just think of how many quarters in a dollar. That just means 4 times per year. that's n. So when we go to plug everything in, we have A equals our initial value, which we said was 9,000, parenthesis 1 plus the rate as a decimal. 1.46% is 0.0146 over n, which is the number of times it's compounded per year, which is 4, to the n, same n, that's up here, and then times t, which is 3 years. Okay, and so we're just going to do this in the calculator. Your calculator actually, you can, especially if you have the newer calculator, you can really put in this entire thing into this, the whole thing. But if you don't have a newer calculator, you're going to have to sort of work your way inside out using your order of operations. So we start with parentheses. I have to do what's in the parentheses, and inside the parentheses, I have to do the division first. So I have to do 0.0146 divided by 4 first. Then that's what that is. And then I have to add the 1, so plus 1. So now that's what this is. And then now I have to do the exponent, which 4 times 3 is 12. So I have to do that to the 12th power. So parentheses, then exponents. Then I can worry about the multiplication, which is now this 9,000 times by 9,000. And so that's my answer. So A would be after 3 years of this, my money in this particular account, I have $9,401.46. Now let me just show you real quick, if you have a fancy new calculator, just how nice this is. I can do 9,000 parenthesis 1 plus alpha y equals from my fraction 0.0146 on top, 4 on the bottom, go out, close my parenthesis, put an exponent of 4 times 3, which is 12, and I get the same, well, relatively the same answer because of rounding. It is slightly off, just because when you did this the long way, there are rounding, there's different rounding things. So this is actually more accurate right here than what we did here. So fancy new calculator, you can do it all in the same thing like that. Otherwise, you'll have to do steps one by one here. Now, we says find the balance after 3 years. Oh, it's changing. Okay, I was trying to figure out what was different about this problem. Find the balance after 3 years if the interest is compounded semi-annually. Semi-annually, if you think of semicircle as half. Half annually means how many times per year? Well, that's 2. So this means n equals twice per year. Semi-annually is twice per year. So you pretty much do the exact same thing above, except your n value is going to be 2. So A equals 9,001 plus 0.0146 over 2, and then 2 times 3. Exactly the same thing. Now I can go up here, redo this, and then just go and change the values. So this is not going to be 4, it's going to be 2. And up here, it's not going to be 2, it's going to be 6. Because 2 times 3 is 6. And then we get 9,000. A equals 9,401. I think you might have caught that. I have to go back to the previous problem. I entered in the wrong thing. I was looking at the wrong problem here. So this one, I think some of you may have caught it and be like, wait a minute, Mr. G, you just typed in the wrong thing. And that is true. I think I typed in 2 here because I was looking at the problem ahead. Let me do that. So 0.0146 divided by 4 plus 1 to the 12th times 9,000. Yep, I sure was. I was looking at the wrong problem. So this is not 9401.46. This is 9402.21. apologize for that mistake, but I was looking ahead and looking at the wrong problem. But you can notice how this one is a little bit higher than this one, and that's because it's compounded more often. The more often that you compound things, the more money you're going to have. So something to think about. And that's why car loans and home loans compound it daily, because they want to charge you the most amount of interest possible. Okay, last problem. I know this has been a long lesson. I appreciate you sort of sticking with me here. This is the very last problem. How long, meaning T, will it take for an initial deposit of 3,000, which is P, reach a balance of 3,000, so balance of 7,500 is going to be A. If 2.5%, which is R, annual interest is compounded weekly. How many weeks are in a year? And it's 52. So everything's in there. You know, we're looking for T. So I have A, which is 7,500. I have P, which is 3,000. I have 1 plus my R as a decimal, 2.5% is 0.025, over the number of times it's compounded per year, times the same N, and the number of years we don't know, T. So just like the previous problems that we did, you know, you want to isolate the exponential part here. I want to isolate this exponential part. So I am going to divide the 3,000 over. And so I get 2.5 equals, parenthesis, 1 plus 0.025, 52, and then 52t. A couple things that you can do. I mean, you could simplify this. If you wanted to simplify what's inside, you could do 0.025 divided by 52 and then add 1. And I mean, you could use that value in there, or you can just keep it as it is. Remember how we did this. This will go into our y1. This will go into our y2. So when I go to put this in the graphing calculator, clear, 2.5 will go there. And then the other one, this is where it gets a little tricky, so you get to sort of put this in parentheses. 1 plus, now if you have an older calculator, you're going to have to put another parentheses, 0.025 divided by 52, close those parentheses, then close the original parentheses. If you don't have, if you have a newer calculator, you can just use your alpha y equals to put the fraction in there. And then I do that to the 52x power. So that's what it looks like. And then I just graph. Now this window is stuck on what we did before, so as soon as this is done, I'll hit zoom 6. There's our 2.5, and there is our compounding. Oh, it's getting close. I do need to go further out. So right now it's going to 10. I'm just going to make my x max to be like maybe 50. Let's see if we can see where that crosses. There's 2.5. And there's my compound, and it crosses right there. Good. We need to see a cross. So calc, intersect, 1, 2, 3. There we go. It intersects at 36.66. So my my t value is 36.66 years. Okay. Please, if you have any questions, let me know. If there was a lot there with compound interest and exponential equations and solving or estimating these solutions, so let me know. Thanks.